This video is brought to you by Hygromo Chalk. Use code TPSA 10% off to get a discount. So this lecture will be about convergence. And from now on in the series, just assume that 0 is not an element of the natural numbers. So if we have a sequence, which is just real numbers labeled x1, x2, x3, all the way up to x infinity, we say that the sequence converges to some point P in R if for any epsilon greater than 0, there exists a natural number n such that xn minus p, the absolute value of that, is less than epsilon for all n greater than big N. So what that's saying is that normally the convention is we take epsilon quite small. So essentially, there's some number n here, which you can think of as quite big, right? Where after a certain point, no matter how small we chose this epsilon, there's going to be a point after which all the numbers in the sequence are going to be close enough to P that their distance between xn and P here is less than that epsilon. So that's kind of, if you to think of it, that's kind of how you would imagine things would converge, how you'd make mathematical sense of that idea that after a point, after any arbitrary point, these points were going to lie arbitrarily close to one another after this, potentially very large number. So we'll write that xn, the sequence, goes to P as n goes to infinity. Or this is what you're more familiar with, is that is the limit as n goes to infinity of xn equals P. An example of a convergence sequence is just xn equals 1 over n. So the first one will be 1, then a half, then a third, then a quarter, and so on. So we claim that this converges to 0. So we see that 1 over n minus 0, the distance between those points, should be less than some small value epsilon. That implies that the absolute value of 1 over n is less than epsilon. N is always positive because it goes to 1, 2, 3. So that's just saying that 1 over n is less than epsilon. And we can always choose some large natural number n such that that will be true. No matter how small epsilon gets, we can just choose an even bigger n, and then 1 over that n will be very small. A very obvious example of a non-convergent sequence is just xn equals n. That's just going to go on and on forever to infinity. It does not converge. So an idea which is quite easy to convince yourself of is that if a sequence, and this is how we can denote a sequence with these curly brackets here, the index n, and then we'd say that n is greater than or equal to 1, meaning that n will go 1, 2, 3. If that sequence is increasing, meaning that each subsequent term in the sequence is greater than or equal to the previous term, and that sequence is bounded from above, then that sequence converges. And similarly, if it's decreasing, so each subsequent term is less than the term before it, and bounded from below, then it also converges. So you can think of if the sequence it's bounded, right? So it's got a maximum. There's no term in this sequence, right? We can think of all of these. We can think of all of these terms in the sequence as forming a set. If that set has an upper bound, and it's constantly increasing, the sequence is always going to be approaching that upper bound, so it must converge because it can't go beyond it. And similarly, if it has a lower bound and it's decreasing, then it's never going to go below that. And then, as a lemma, every convergence sequence of real numbers is bounded. So, which again makes sense to think about. If you had a convergence sequence of real numbers that was unbounded, well, how could it ever converge to anything? Now, a useful idea is the idea of a subsequence. So if we had a sequence x1, x2 in all the real numbers, a subsequence of that sequence is just, well, formally a sequence of the form xj1, xj2, xj3 with j1 less than j2 less than j3. But in reality, it's just following some rule, you just select certain elements of the sequence and then order them with their indices in ascending order. So yes, example would be x1, x4, x9, x16. So a rule could just be you take the index and you square it, or x2, x4, x6, x8. So just all the even ones. And this leads to a very important result called the Bolzano-Weierstrass theorem. So the Bolzano-Weierstrass theorem is a very powerful result that states that every bounded sequence in R has a convergent subsequence. So no matter what the sequence is, if it's bounded above or below, then it has a convergent subsequence. For example, if we have xn equals -1 to the n, that sequence you can see sort of just like flip-flops between -1 and 1. You can see this, if it's the n-axis, it would sort of just zigzag along. But if we just take every odd, or in this case every even index, then we'll just get 1, 1, 1, 1, which just obviously converges to 1. And we also have this result, the squeeze theorem. So if we have three sequences, an, bn, and cn, such that an is always less than bn, and bn is always less than cn, then, and we have that an is converging to p, and cn is also converging to p, that means that bn will also converge to p. So you can sort of see here, if we had like the n-axis there, if bn was always squeezed between some an and cn, and they both converge to the same thing, p, then bn will also converge to p. This can be very useful if the sequence itself, bn, is kind of hard to work with, but if you can prove that it's always, it's bounded from above and below by some other easier sequences that have the same limit, then you have a way to find the limit of bn without actually having to work with it directly. Okay, so now we're going to the same concepts but the multi-dimensional version. So let's say we had a sequence of points in Rd, or you can think of them as vectors, and then that will converge to a point P in Rd if, and it's the exact same definition, for any epsilon greater than 0, there exists some natural number such that always after that natural number, the points in the sequence are going to be within an epsilon distance of point P. Now, in this case, this here, the two lines represent the vector norm, not the absolute value. And just remind you that's the formula for it here. And again, we just say that the limit as n goes to infinity of xn is p, if this holds true. So how you can imagine this, I've drawn it here in R2. The sequence of points can do any crazy behavior that doesn't look like it's going to converge until a certain point, n. This should just be a regular n. But after this point n, so you can see here it's not really converging, it's going to go around. Now here in the middle is the point P, and I've drawn around it a ball, an open ball of radius epsilon. So for all points after this point here, xn, you can see that it begins to stay inside this ball of radius epsilon. Now epsilon could shrink and be a tiny ball, and it actually shouldn't matter how much this ball shrinks around it, we'll be able to find some point xn after which the points in there will stay inside that ball, and that's how we can imagine series converging in multi-dimensional space. Now, how you actually do this in practice is actually really easy because you just look at the components. So if we write out as components here, P1 to PD is a point in which a sequence xn is converging to, well then that's completely equivalent to the individual components of each vector in the sequence converging to the corresponding component in the limit. So so the ith component of the first vector in the sequence and the ith component of the second, third, so on and so forth, should converge to the ith component of the limit point. That's how you kind of handle it when you're actually doing the maths. We say that a sequence of vectors is bounded if there exists some m such that the norm of this of all the vectors in the sequence lie within m. So m is just some ball centered on the origin, and all the points in the sequence stay within that ball. So that's how we generalize the idea of boundedness, because of course there's no real above and below in RD, because you can't completely order all the points. So this is the equivalent definition. All the points, you can draw some, so even here, if the origin was here, we can still draw some massive circle here, and then all the points will stay within that, and then it's bounded. So essentially, we wouldn't be able to see if it was unbounded, because there could be some point that would be shooting off towards infinity. And the multidimensional Poisson-Weierstrass theorem says that every bounded set of points in RD has a convergence subsequence. And this certainly wasn't very obvious to me when I first came across it. The proof is very lengthy, but it actually just mainly uses the one-dimensional proof as the sort of base. It's very, very useful. I put an example here. So in R2, if we took xn to be this, the x component would be, or the first component would be sine of n pi over 2, and the second component would be cos of n pi over 2. And I just drawn out the first 6 points for you here. You can see that we kind of start here on the unit circle, and we sort of move around in this clockwise fashion. I just showed that the sequence is bounded, which should be fairly obvious. You just take the norm of the points, and because it's sine and cosine, they have this times relation where this just aggregates to 1. So the sequence is in fact bounded by 1, it stays within the unit circle. So therefore, it's a bounded sequence. We can take a convergent subsequence, and you'll notice that x1 and x5 have the same value, so there's x2 and x6. So we can actually just take any xi, and then xi plus 4, xi plus 8, xi plus 12. So xi plus 4k, where k is an integer, that will be a convergent subsequence of the sequence. So we'll just say this point, this point, this point. And that's its application, a fairly basic one, of the Poisson-Weierstrass theorem in 2 dimensions.